Let's go over some notes on algorithms, pseudocode, and flowcharts. Most first-level programming books, when you go over an algorithm, will show you a recipe. A recipe represents an algorithm. Your input are your ingredients. You need to follow your steps in the order that they are written. Otherwise, you won't get the correct output. In the context of computer programming, an algorithm is defined as a well-ordered collection of unambiguous and effectively computable operations that, when executed, produces a result and halts in a finite amount of time. These are all the qualities of a good algorithm: that it's well-ordered, the steps are in clear order, unambiguous, you're not questioning what the step means, and the operations described are understood by a computing agent without further simplification, such as creating an integer variable and setting it equal to 6. Effectively computable, the computing agent can actually carry out the operation. It's something that our computer can do, such as a branching statement or a loop. Method for developing our algorithms. There are many methods to develop algorithms, but this is one way that works pretty well. First, define the problem. State the problem you are trying to solve in clear and concise terms. This is easy for us in first-level programming because the programming problem is always given to us by our author or by our instructor. List the inputs, information needed to solve the problem. What are your inputs? What data are you given? And then you ask yourself what your output should look like. What output do you want from your algorithm? Then write down the steps to get from point A, your input, to point B, your output. This is the part that takes a little bit of practice. But if you keep practicing with smaller and easier algorithms, when the harder algorithms arise, you'll be able to solve them too. And always test that your algorithm works. You can test with a pen and paper, and this is called desktop testing. Inside the notes on algorithms are some key words that you can use while writing your algorithms, and you can read through this. We'll also use pseudocode to write our algorithms. It's a shorthand way to write a step of an algorithm that is easily translatable into programming code. Inside the notes on algorithms are also some other variations of if, else, and switch. Note that they look like our programming code, and you'll indent your algorithm the way that's specified here or in some kind of logical order similar to this. Here's a great pseudocode example. Express an algorithm to get two numbers from the user, dividend and divisor, testing to make sure that the divisor's number is not 0, and displaying their quotient using pseudocode. So this is our problem. It's defined for us. So what is our input? Our input is given to us by the user. It's our dividend and our divisor. What is our output? Our output is their quotient. How do we get from point A to point B? Here are our steps. Step 1, declare your variables, dividend, divisor, and quotient. When we're writing our algorithm, this is an optional step. A lot of times I'll write this as step 0. Step 2, prompt the user to enter the dividend and divisor. Note that this is 2 steps, but we're writing it as 1, and that's fine to do. Get the dividend and divisor. And now here comes some of our Now here's some of the syntax that we saw above used in this algorithm. We have the keyword if, and then we're writing out in plain English our Boolean check, which is divisor is equal to 0. We write the keyword then. Now what comes after is the true part of this branching statement. What goes in do while is a substep of the do while statement, so you can see it's indented again and using substep numbers. Display your error message, divisor must not be 0. Prompt the user to enter a divisor, get that divisor, and here's the wild part. Divisor is equal to 0. So we know if this is true that it'll go back to step 4.1. Then write the end if. I always say this is an optional step. Display your dividend and divisor. With step 6 and step 7, calculate your quotient as dividend divided by divisor. Here's a little bit of pseudocode. And display your quotient. We've gotten from our input to our output. Now let's learn about flowcharts. When you're learning flowcharts, you only have to know a few symbols. There's the rectangle, which describes a process, such as make a variable or initialize a variable. We have slanted rectangles that are used to show our input and our output. Then we have diamonds. These are our decision symbols. They're used for Boolean statements only and should always have 2 arrows coming out of them. If you have 1 arrow coming out of your diamond, it probably should not be there. Then we have a connector. Then we have a terminal. Terminals are used for our start and our stop. And then we have our flow lines. Let's look at an example. So here inside Notes on Algorithms are some ways to draw your flowcharts that you can look at. But the best way to learn is to look at an example. Here's our flowchart example. It's the same algorithm as above. We're getting 2 numbers from the user and testing to make sure the divisor number is not 0, and then displaying their quotient. So we have our start and our stop drawn as ovals. Then we have our rectangle, where we're declaring our variables, dividend, divisor, and quotient. Notice the flow line flowing down out of the rectangles. Remember that rectangles can only have 1 arrow coming out of them, and if they have 2 arrows coming out of them, they should probably be a diamond. When we're prompting the user or getting the dividend and divisor, notice it's a slanted rectangle for input and output. Now comes our Boolean check. If the divisor is equal to 0, notice they only used a single equal sign, which would lead to a logic error in programming, but in a flowchart, it's all right. So we have our yes arrow and our no arrow. Always 2 arrows coming out of a diamond. If the divisor is equal to 0, we go down this flow line. We output an error message, prompt the user, and get our dividend divisor again. Notice our arrow that flows out of that last rectangle and up to the Boolean check yet again. This is our loop. If it's a no, then we calculate the quotient as dividend and divisor, divided by divisor, and then display that quotient. And then we stop. Remember the other rule about flowcharts. You should never have any pathway that dead ends and doesn't get to the stop. Every path should lead you to the stop terminal. Let's practice writing some algorithms, and then we'll practice making a flowchart. This is your lab. The questions that we don't complete here, you will be responsible for completing on your own. You'll need to answer these questions. Let's look at this example that's done for us. Write an algorithm to raise any number to the 3rd power. Well, what's our input? Our input's any number, an int entered by the user. What's our output? Any number raised to the 3rd power. How do we get from point A to point B? Here are some steps. Step 1, input in any number from the user. Step 2, here's some pseudocode. Int base is set equal to any number. Step 3, for exponent from 1 to 3, this is a for loop. Any number is assigned the value of any number times base. This repeats 3 times. Step 4, output any number. Notice it's written in a little bit different style than our notes on algorithms, but this is still a clear and logical way to write this algorithm. Let's do letter C together. Letter C says, write an algorithm to produce the first 15 numbers of this series. 1, 1, 2, 3, 5, 8, 13, 21. Notice the pattern. First number plus the second number equals the third number. First number plus the second number equals the third number. This number plus this number equals that number. This number plus this number equals that number. You get it. This is the Fibonacci sequence. Let's write the algorithm for this together. I'm going to go ahead and write it in Microsoft Word. So our input to this problem are the first two numbers. And we'll call them number 1, and we'll assign it the value of 1, and we'll call it number 2. Now how did I know to come up with these two numbers? Well, looking at my pattern, I know I need at least two variables, because I'm going to have to add this one plus this one equals the third number here. So it makes sense that I would have a variable called number 1. And so I decided, hey, let's try this. Let's make a variable called number 1 and set it equal to 1, and number 2 and set it equal to 2. Now, will you get your algorithm right every single time on the first try? No. That's what makes algorithm design fun. You get to try new things. All right, what is our output? Our output is the Fibonacci sequence. How do we get from point A to point B? Let's complete step 1. Let's see, what would be a good step? This is where you have to use your creative mind. Let's see, I'll have a number called number 3, and I'll set it equal to number 1 and number 2. So let's see, I'll say create a number 3, and assign it the value of number 1 added to number 2. All right. What would be a good next step? Well, I could output number 1, number 2, and then number 3. Let's try that. So I'll say output number 1, and then I can use my copy and paste skills, because I know I mightn't have to change these steps, so I'm going to make them separate steps. So I'll make this step 3 and this step 4. And I'll just output these numbers. Now it's good to keep track, and this is what's called desktop testing. Keep track and make a picture of what you're doing in your algorithm so that you can visualize what's happening. Alright, we have a number called number 1, and we have it equal to 1. We have a number called number 2, and it's equal to 1. Now let's do our algorithm. Create a number called 3, and assign it the value of number 1 plus number 2. So number 3 is a 2. We'll output number 1. So we'll output our 1. That looks good. We output number 2. We output number 2. We output number 3. Okay, all is well. Now what would be a good next step? Let's look at that algorithm again. Now we're going to output a 3. How are we going to get the number 3? Let's see. Number 2 plus number 3, and then maybe put it in number 1? Or how about number 1 plus number 2, and then put it inside number 3? That seems like a good idea. Let's write that as a step and try it out. So let's write down a step and try it out. Let's say number 2 is assigned the value of number 3. Let's see what happens then. Number 2 is assigned the value of number 3. Okay, that looks good. Now what if I went back up to step 1? Because the number 3 could equal a 3. Let's try that step. So here, I'm just going to go ahead and write, since I'm just writing out this algorithm, and say go back to step 1. Now later on I can make this look pretty in the do while loop, but for now I'm just going to write that down. So if I go back to step 1, I would then run this algorithm line. Number 3 equals number 1 plus number 2. So now he'd equal 3. Alright, now I need number 3 to output. I need that 3 to output so that it'll look like my Fibonacci sequence. But in my algorithm, I'm outputting number 1 and number 2 again. What if I moved these steps up here, out of the way, so that way I could just output number 3. And so that way, when I get to this step, and I need to output this number 3, and it'll look like my Fibonacci sequence. But maybe that'll ruin the beginning of my algorithm. So let me start over. And this is called desktop testing. When you're desktop testing, you start to write your algorithm. You can guess a step. You write that step down, and then you visualize, or draw pictures, or write down what it's doing. If that step's wrong, you add another step, or you move that step, or you edit that step. This is called your design iteration. Sometimes you can have a fast design iteration and finish your algorithm in no time. Sometimes it takes days to finish an algorithm. Don't get frustrated. Keep trying new things and fail fast. Alright, let's try it again. Number 1 equals 1. Number 2 equals 1. Let's go to our steps. Now my step numbers are all messed up, but just ignore them for a while. Output number 1. Alright, he outputs a 1. Output number 2. He outputs that 1. Create a number 3 and set it equal to number 1 plus number 2. Okay, we got that far. So now number 3 has the number 2 inside of it. Then we output number 3. Now set number 2 equal to number 3. So I'll go ahead and put the value of 2 inside of our variable number 2. Now go back to step 1. Remember, it's this step 1 here. Set number 3 equal to number 1 plus number 2. So we'll go ahead and put a 3 in here. Hey, this seems to be working. Let's go to the next step. Output that number 3. That looks good. Number 2 equals number 3. Alright, now let's go back to step 1. Number 3 equals number 1 plus number 2. Uh-oh, number 3 is going to equal 4 now. We must have done something wrong. Let's think about it. Number 1 didn't change. We need number 1 to change into something so that we could add it to number 2, and number 3 could be the correct number, which is 5. What if we let number 1 equal the old value of number 2 before number 2 got set equal to what number 3 was? We need to do that step right here before we set number 2 equal to number 3. So we'll need a step right here. Let's try it. Number 1 will equal number 2. So let's begin again. Remember desktop testing, you iterate, and you try things again. Alright, output number 1 and output number 2. There's our 1 and our 1. Then we have our number 3 set equal to number 1 plus number 2. We output our number 3. Looking good. Now number 1 equals number 2. This time around it's going to equal a 1. Number 2 equals number 3. Go back to step 1. Number 3 equals number 1 plus number 2. Looking good. Output number 3. Here's where we change things. Number 1 is assigned the value of number 2. Ah, yes, he became that 2. Number 2 is assigned the value of number 3. Moving the numbers over. Go back to step 1. Number 3 equals number 1 plus number 2. Ah, yes, now we get the 5. Output number 3. Number 1 equals number 2. Moving it over. Number 2 equals number 3. Moving it down. Go back to step 1. Number 3 equals number 1 plus number 2. Ah, yes, I think we have the Fibonacci sequence down. Now this will go on forever. We haven't made this a finite amount of steps. What did our algorithm say? Our algorithm read to get the first 15 numbers of this series. So let's clean up our algorithm and make a loop and have it iterate 15 times. Let's see, which parts do I want to iterate? These parts here. Go back to step 1. This will be my loop. Let's clean up these steps. Alright, I've put our steps that we wanted to repeat inside of a do while, and I've cleaned up the step numbers. Now it says, while go back to step 1, I need this to be a Boolean check that'll tell me to do this loop 15 times. I need to make a count variable. A count variable that can iterate for this loop 15 times. I'll go ahead and add this count to my variable declaration list, and I'll set them equal to 10. Let's see. I need to decrement this variable inside of my loop and then check that he's greater than 0. I'll add a step here at the end of the loop, 3.5. I can write some pseudocode to subtract 1 from my count. Now I can say while count is greater than 0. And this will make my loop iterate 10 times. Let's see, I want it to iterate 15 times. Will this output 15 numbers? Let me look. Number 1 and number 2 were output outside of my loop. This is actually going to iterate 15 other numbers, 17 in all. I think I should change this to 13. Now it'll be 13 iterations of my loop, printing out 13 times number 3, plus my number 1 and my number 2, which were output outside of the loop. 15 numbers in our Fibonacci sequence. There's my algorithm. Alright, I'll let you write these two algorithms. Now this algorithm traditionally a lot of students have had trouble with. So let's practice writing this algorithm. Remember that we practice with these simpler ones so that when we do get into an algorithm that's a little bit difficult for us, we'll be able to solve it. The more algorithms you solve, the better you'll get at it. Write an algorithm to play a number guessing game with the user. The user is given 10 chances to guess a 4-digit number. If they get any of the digits correct in a guess, then the program will output the number of digits correct and the sum of those digits. And so it's a guessing game that kind of works like this. We have a secret number that's 4 digits. And for this problem, let's say that we're not going to repeat any of those digits. It makes the algorithm a little bit harder if we say that we can have repeats. Now the user is going to give us a 4-digit guess. What we're going to do is we're going to look at the digits in the 4-digit guess. And if they get any of the digits that are the same as the secret number, we're going to count them and then sum up those digits and then output that to the user. So if the user guessed 1589, they got 1 digit right, which is the number 1. So they got one digit right. The sum of the digits is the number 1, so is a sum of 1. We output 1 to the user. Now if the user is smart, which we all know she is, we would deduce that we have the 1 as the correct digit. So now we would guess some different digits. So maybe we would guess 1, 2, 6, 7. The computer would then look at our secret number, look at our user guess, and deduce that we have the 1 and the 2 correct. So now we have 2 digits correct, and the sum of those digits is 3. We would output 3 to the user. The user then knows that we have the digits 1 and 2 correct, because it's the only digits that would sum to 3. Maybe the user guesses then 1, 2. The number of correct digits would output as 3, and the sum of those digits would output as 7. You get the picture of how this game is played. They are given 10 chances to guess that secret number, and it's like a little game. Let's write the algorithm together to solve this. We'll go ahead and start up our algorithm with a step 0. We know we're going to need some variables because we've drawn our picture, and we know that we need to keep track of these things here. So we know we need to declare secret number, now let's think about what we want to do for step 1. What would be the first thing that we would need to do? Let's assume that our secret number is already set up. Ah yes, we need to get the user guess. We've put a default in here, but we really should ask the user for it. We would get the user guess. Alright, what would be our next step? Well, we can't say something ambiguous like check all the digits against all the secret number digits, because that's not easily computable. A lot of times we have to think about what our brains are doing in slow motion to understand what to do for the next part of the algorithm. What did our brain do to check, to see whether the digit in user guess was equal to any of the digits in secret number? Ah yes, it took the first digit, or even last digit, it took one of these digits, and it used that digit and it compared it to each and every digit one at a time inside of secret number. If one of them was true, my brain alerted me to that fact, and then I could sum it and count it. Now, knowing programming, you could get either the first digit over here or the last digit over here pretty easily. So we could write our algorithm either way. But let's go ahead and get this first digit on the right out. We'll say, take the digit on the right, or the rightmost digit, of user guess, and maybe assign it to a variable. That's a good idea. So we'll say create right digit and set it equal to the digit on the right of user guess. That looks like a good step. Let's do step 3. Now what did I do with that digit? I wanted to compare that digit to each digit inside of secret number one at a time. So I know I'm going to have to repeat these steps. I know I'm going to have to do it 4 times. So I could even write a for loop here. I could say for I from 1 to 4, or even 0 to 3. That would still iterate 4 times, and it's more programming-like. Now I'd want to do some sub-steps. What do I want to do more than one time? I want to compare right digit and see if it's equal to the digit at index I. So this could be my 0 index, 1, 2, and 3, or even if I go from left to right, 0, 1, 2, 3, the algorithm works both ways, and see if it's equal to the digit in secret num at index I. Now I'm going to get a sub-step, because if this is true, I want to go to this inner sub-step. What if it is true? What if one of these numbers was a 3? If 3 was equal to 3, what do I want to do? Well, I want to count it. So I can write some pseudocode to increment my count. I also would like to add it to my variable SUMCorrectDigits. So I can even write some pseudocode for that. Alright, that's looking pretty good. Then, what do I want to do? I only want to do those two things if it's equal. And I have it in a loop where it's checking each digit. So I think that looks pretty good. So I'll come out here. And what would I want to do next? Probably repeat step 2. Let's go through an iteration and draw out what's happening inside of our algorithm so far. Let's visualize our algorithm. Get the user guess. Let's say the user guesses 1, 2, 3, 4, or 0, 1, 2, 3. Let's say the user guesses 0, 1, 2, 3. We'll get the user guess. Create right digit and set it equal to the digit on the right of user guess. We'll worry about how to implement that later. Let's see, it's a 3. So we'll need to create a variable called right digit. And we set it equal to 3. Now for I from 0 to 3, we're going to repeat this 4 times. Compare right digit and see if it's equal to digit in secret number at index I. So I'll compare the 3 to the 6. Nope. 3 to the 3, yes. I go into my sub-step. I count it. I get a 1. And I sum it instead of sum of correct digits. That looks great. Now what step do I want to do? I know. I want to get the next digit out of user guess. Well, that's repeating a step. Maybe I could do something instead. Maybe I could go back up to step 2. But then I'm getting the 3 again. I know. I'll take the 3 out of there. Then when I go back up to step 2, I could get the next digit, which is the number 2. That looks like a good step. So I'll say in step 4, get rid of the number on the right. Get rid of the digit on the right most position in user guess. That looks good. Now step 5 would be go back to step 2. Now whenever I have a step that says go back to step 2, I know that this is going to be inside of a loop. So I know that these steps will be inside of that loop. Alright. I can make another step here. Make this my do step. Now, how many times do I want to do this step? Well, I have 4 digits that are going to be on the right inside of user guess. I need to do this 4 times. I can make this a for loop, or since I've already got a do while, and I can kind of think ahead, that when I get rid of the rightmost digit the last time around, user guess will equal 0. So maybe while user guess doesn't equal 0 or is greater than 0. So, what parts do I want to repeat for his try? Yes, I need to get the user guess again. So I need, after step 5, to go back up to step 1. I'm getting pretty good at these do-while loops. I bet I could make this into a do-while loop. So I'll go ahead and put my step up here and write do. Now all of these are going to be inside of that step. I'll go ahead and write here my while part. I'll worry about the step numbers later. Now I want the user to get to do his user guess and check that number 10 times. Let's go ahead and create a variable called count. We'll start him out at 0. And then we can use count and count him each time. And when he gets to 10, we know to stop. So I know I'm going to need a step in here to increment my count. And I want to complete or do this loop while count is less than 10. Okay, that looks pretty good. Let's do a run through of our algorithm again. Let's start up here. We declared our numbers, and we have them here declared and initialized as we said in step 0. Now we have this other step here, and we make a variable called count, and we set it equal to 0. So when I'm writing up my algorithm, I'll go ahead and make a variable called count and set it equal to 0. Now I'll go into my do-while loop. Get the user guess. Let's say the user types in 9, 1, 2, 3. We jump into our do while loop. We create a right digit and we assign it the value of the digit on the right of user guess. So it would be the number 3. Now for I from 0 to 3. So we're going to do these steps 4 times. We compare the right digit and see if it's equal to the digit in secret num at index I. So we take this rightmost digit, 3, and we see if it equals a 6. Nope. So this if statement isn't true, so we repeat the step again. But now we're at index 1. Compare right digit, 3, to index 1, which is a 3. Yes, they do equal each other. So now we go into the substep. We up our count by 1, and then we add that right digit into some correct digits. 3 plus 0 is 3. Now we compare the 3 to the 8, nope. And now we compare the 3 to the 9, nope. And so now we finish our for loop step. Now we'll go to this step. Now, kind of ignore the step numbers right now. Just use your indentations. Get rid of the digit on the rightmost position inside of user guess. Alright, so we'll get rid of that 3. Now, we check user guess. Is it greater than 0? Yes, it is. We come up here and repeat this step. Create the right digit and assign it the value of the digit on the right of user guess. Alright, it'll be assigned a 2. Now I'm going to repeat this 4 times. I'm going to compare that right digit and see if it's equal to the digit in secret num at that index. So is 2 equal to 6? No. Is 2 equal to 3? No. Is 2 equal to 8? No. Is 2 equal to 9? No. Alright, that's my for loop. Get rid of the digit on the rightmost position in user guess. get rid of that digit. I check to see if user guess is greater than 0. It is. And now we can start to remember these steps. We take that rightmost digit and put it into our variable right digit. So we would take the 1 and put it into our right digit. We then compare 1 to 6, and then 3, and then 8, and then 9. And then we get rid of that 1 inside of user guess. We repeat, because user guess is still greater than 0. We get that rightmost digit, which happens to be a 9. We then compare it to the 6, nope, the 3, nope, the 8, nope, and then finally we say yes, that 9 is equal to that 9. So we'll go here, we're going to up our count, and then we add that 9 into our sum of correct digits. Get rid of that digit. And now user guess is not greater than 0. I just realized I was using this count for the count that was controlling my loop. The count that's controlling my loop is actually user guess, number of user guesses left. So I need to declare another variable here called number user guesses. And make sure it's initialized to 0. And then it was that count that we're incrementing here, and it's that count that we're checking is less than 10. Alright, we made it out of this one here because our user guess was equal to 0. So now we up our number of user guesses, which was a new variable that we had to create. We started out at 0, and now we're going to increment him. And now we check. Alright, yep, we're still going to do this again. And we are going to go up here, and we're going to get the user guess again. So let's say the user is pretty smart. Wait a second here. We didn't output anything. How does the user know what to guess next? We need to write that step in here. We need to output our count and our sum of correct digits, so then the user can guess again intelligently. So we need to write that step in here. Note that we'll write that step down here when we know what our count and sum of correct digits is equaling. So here we'll output our count and our sum of correct digits. Alright. So back on track here. We outputted our 2 and our 12. So now our user can look at his old guess, which remember had the 9 and the 3 in it, and he would deduce that maybe the 9 and the 3, since it outputted 2 digits, must be the 2 digits that was used inside of the user guess that were correct. So our user is pretty smart, and now he's going to guess a 9, a 3, a 7, and a 2. Alright, let's go through the steps of our algorithm. We'll get that rightmost digit, which is a 2. We then compare it to the 6, and then the 3, and then the 8, and the 9. It doesn't equal any of those, so this will never be true. We then get rid of that rightmost digit. We check that it's greater than 0, and we come up here. We set right digit equal to that rightmost digit, 7. We then check the 7 against the 6, and then the 3, and then the 8, and the 9. It doesn't equal any of those, and so we repeat our steps. Now we'll set right digit to 3. Now here's where there's going to be a true case when we get here to 3. What does our step tell us to do? It tells us to up our count. Uh-oh, our count is still 2. What did I forget to do in my algorithm? This is a new guess. If I let it equal 2 already, when it outputs, it'll be 2 off than the correct amount that it should output. I need to reset count back to 0 before I increment it here. But I don't want to set it equal to 0 in here, otherwise it'll set it to 0 every single time this is true. And I don't want to set it equal to 0 before I output it. I want to set it equal to 0 after I output it. That way I don't ruin it. So I'll go ahead and reset them, or assigning the value of 0. And I can write some pseudocode to do that. So that way when it comes time to increment, or add two sum of correct digits, it'll add and increment correctly. Alright, that seems to work. So when I increment, I'll increment 1 up, and my sum of correct digits will start out at 0. So then when I add the 3 in there, it'll only equal 3. I do the next step in my algorithm, and I see that 9 is in the number. Now when I increment my count, it'll be a 2, and when I add them to sum of correct digits, it'll be a 12. Then when I output them again, it'll output the correct result, which is a 2 and a 12 again, because those other two numbers were not inside of my secret number. Alright, this algorithm seems to be working. And actually it is. So now I need to clean it up a little bit. You can keep that step 0. And remember before you turn them in, to take some time to clean up your step numbers. Well, it's almost correct. Let's think about the case that the user actually types in the secret number. It'll add up the count as 4, and he'll sum up those digits okay, but does it ever tell them that they actually won? We should actually check to see if the count is 4, we should output if they won or not. So, down here, before we reset it, and maybe even before we output it, we should check to see if that count equals 4. Now what if the count equals 4? What do I want to do? Well, I want to output that they won. And then maybe even end my game. There, that seems to work. If the count is 4, then I'll output that they won and end my game. If not, I'll continue on. But what if they get past 10 guesses? Shouldn't I output if they lost also? Yes, probably. So here's where I would output that they lost. Now that seems very complete. That way, a user can actually play the game and win or lose. Now you will get extra credit if you actually implement this algorithm, which means translate every step into a line of programming code. It should be pretty easy. To implement an algorithm is the easy part. Every step equals 1 or 2 lines of code. Alright, good luck implementing.